Hey everyone, I'm Zhang Yuxu. Today I will present our work CoRoPy, a geo-distributed edge compute solution for space-time vehicle tracking. Space-time vehicle tracking is to create a space-time track of suspicious vehicles using camera networks in a city. The motivation is manually finding a track of a vehicle across multiple camera feeds can be label-intensive and error-prone. That's why we want an intelligent system to replace the manual label and aid human decision-making. Specifically, the goal of CoRoPy is to explore the design space for such a smart camera system that live camera streams are processed locally in just-in-time, and the cameras cooperate with each other to build up the trajectory of all the vehicles in real time. Cameras considered in our systems are statically and geographically distributed. Each camera has its own computational resources, and we have a horizontal network resource between the computational resource of each camera. The contribution of CoRoPy includes a scalable by design distributed edge architecture, which allows flexible computer vision components by domain experts. We make use of the idea of bounded horizontal communication to also bound the computation on each camera. We have autonomous camera topology management to handle the camera failures. We make careful design considerations for scalable implementation. We have a proof of concept implementation of CoRoPy based on Raspberry Pis and Coral TPU. We did an in-situ evaluation of CoRoPy using video streams from real-world cameras and simulation. The following of a talk would cover the functional decomposition of CoRoPy, the placement of functional components, and implementation and performance evaluation of CoRoPy. Let's first look at functional decomposition of CoRoPy. We decompose CoRoPy into 5 functional components. Among them, vehicle identification, communication, and vehicle reidentification are running locally and concurrently for each camera. The other 2, camera topology server and storage, are shared between cameras. Next, we use a real-world example to show how CoRoPy constructs the trajectory of all vehicles in real time. When camera join the system, each camera will send its longitude and latitude information to the camera topology server. Server will then return the topology information for each camera. For example, this topology information indicates for vehicle moving from right to left, camera B is the downstream camera of camera A, and camera C is the downstream camera of camera B. After camera join the system, every camera will doing vehicle identification locally and concurrently. The goal of vehicle identification is to identify a vehicle entering the camera's field of view. And when a vehicle is leaving the camera, for example, the red vehicle is leaving camera A will generate a unique detection event for the red vehicle. The detection event has 3 purposes. First purpose is for communication. Based on topology information, camera A will forward this detection event to camera B's candidate pool to inform camera B the red vehicle is heading towards you. Similarly, later, when the green van is leaving the camera A will also forward its detection event to camera B. Notice, meanwhile, there are other vehicles leaving the camera A in the opposite direction. Their detection event will not be forwarded to camera B. The second purpose of detection event is vehicle reidentification. Now, let's look at the computation happening on camera B. When camera B detects the red vehicle is leaving the camera, it will first send detection event B7 to camera C, then it will match B7 with the detection event A0 in its candidate pool using the features. Similarly, when the next green van is detected by the camera B, its detection event B9 will also match with detection event A2 in the candidate pool. However, because the gray van is turning into the parking lot, the camera B will not forward B9 to camera C. Eventually, when camera C detects the red vehicle, it will match the category event C12 with the B7 in its candidate pool. The last purpose of the detection event is storage. We store the trajectory of all the vehicles as a graph, where the vertex is detection event and the edge is a successful matching between two detection events. We allow multiple incoming and outgoing edges for false positives formation techniques, and we do frame storage for traceability of our application. Next, we're showing the placement of these functional components on our system architecture. From our preliminary experiment, we found live processing speed should be faster than 10 frames per second to achieve good results, which implies every subtask should cost less than 100 milliseconds. The second goal of placement is scalability. With this in CorePy, we decided to place all the heavy lifting real-time processing on device to achieve the deterministic latency bound and to have no pressure on the backhaul network bandwidth. And we heavily use the pipeline processing on device to exploit the parallelism to achieve the 100 milliseconds latency bound. Next, we're offloading the storage to a nearby edge. The reason is because limited resource devices like Raspberry Pis has limited storage capacity, which incurs a high on-device storage overhead. Notice we send frame to edge asynchronously, which means storage is no longer at the critical path of pipeline processing. Finally, we place the camera to the server on cloud because cloud have global knowledge to maintain the geographic relationship between the cameras. Topology change is infrequent. It happens when a new camera is deployed or an older camera is removed. Next, we'll show the implementation and performance evaluation of CorePy. Pipeline processing for each camera spans across 2 Raspberry Pis and 1 edge Coral TPU. In this work, we focus on the system-side issues, so we choose to use the off-the-shelf vision techniques. CorePy is implemented in Python, and we use ZeroMQ for communication between device, edge, and cloud. We use 5 on-campus roadside cameras to build a real-world testbed. And for controlled experiment, we use 2,000 frames from each camera with labeled ground truth. Our work includes 5 evaluation hypotheses. Due to time limitation, we will only show the first one in this presentation, which is the processing speed should be faster than 10 frames per second. This micro benchmark shows the latency for each subtask happening on one camera, which span across 2 Raspberry Pis. Here we can show the 2 cost operation is load operation and inference operation. While inference is expected because it's a deep learning method, load is not expected. This shows image decoding and encoding is inefficient on Pi and becomes the bottleneck of the processing pipeline. Overall, we achieve a processing speed of 10.4 frames per second. As conclusion, in this work, we built an end-to-end distributed system called CorePy to create a space-time track of suspicious vehicles in real time. We implement CorePy on Raspberry Pis and Coral TPUs. We do an in-situ simulation with both real-world cameras and simulation to show the practicality and scalability of CorePy. As future work, first we want to look for low-cost and better vehicle re-identification algorithms besides color histogram. Next, we want to look for service computing to scale the results for each camera based on the number of activities happening within each camera. That's all. Thank you for coming to my presentation.